Hello. Good afternoon. If you were at my last talk, hello again. And if you weren't, let's start with a bit about myself. Can the back row hear me okay? Perfect, thank you. My name's Isaac. I live in Estonia. I'm currently a research engineer at Clarify, and I help build and maintain multimodal retrieval systems on our AI platform. These days, I'm working on improving our vector search capabilities and enabling new generative AI tech in production. My background was in aerospace engineering, so the plane, and I took a few hops to land in AI. So today, we're going to talk about deploying LLMs by ourselves, and so thank you for Gabrielle and Maria for setting the stage up. You have all the data and the models. Now we're trying to deploy that. I wanted to start with some motivation behind this topic as well. So at work, before we started figuring out how to serve all these LLMs, our focus was on computer vision. We were serving models for users to do stuff like image recognition, detection, and tracking. And so most of these models were quite small, and they're at most a few hundred megabytes. So the problem we wanted to solve was how to bin pack them in a way that uses the resources well and still be a robust enough system. In addition, we also had to manage dependencies, especially stuff like Torch and NumPy, but sometimes it's not smooth sailing, as you can see in this example. But sometimes these different versions would lead to conflicts that causes downstream problems. So it could be quite frustrating to align Python, NumPy, Torch, and CUDA driver versions. That's why I think maintenance and reproducibility have always been a hard problem in the machine learning community. As we started serving LLMs, we found a slightly different set of challenges. LLMs are huge and have complex architectures, which make them a slightly different beast than computer vision models. So why, you ask? Why not just use OpenAI or another cloud provider? Mainly this is because we have upstream requirements from our customers to deploy on premises or air-gapped systems. So that was a hard, not negotiable item. So raise your hand if you have deployed at least one LLM before. Oh, a few in the crowd, great. How about on your laptop? Okay, same few people, great. What about in production? Okay, great, awesome, great. I mean, you guys probably know, right? Like, how hard could it be? As it turns out, there are quite a few challenges if we have normal people constraints, as both Maria and Gabrielle pointed out. So let's take a look at what they are and what we can do about them. The first challenge is, of course, with computational resources and their costs. Historically, when we train a neural network, each parameter is represented by a float 32, or actually now it's more float 16 if you look on Hugging Face. So let's use that for estimation. For a model like llama-cpp-python, we're talking about 130 gigabytes for its model weights. So instead of trying to fit many models into a GPU, like the one we saw, like the problem we saw before, we're now trying to find a big enough GPU that can fit one model. And can you name a machine that can easily fit something like this? I know that my MacBook definitely cannot. We also know that most good GPUs can be quite expensive to procure and maintain. And the free GPUs have time limits, like Colab. There are also other ongoing challenges like optimizing resource utilization and managing hardware infrastructure to handle peak loads efficiently. The second challenge is with latency and throughput. In real-time LLM applications, maintaining low latency and high throughput are quite important factors in user satisfaction. For instance, imagine that this is the speed of your chatbot. Would your users be happy with that experience? Likely not. Generally, smaller models like 7B are associated with higher throughput and faster time to first token, but the output quality would not compare to that of a 70B model. So there's a clear trade-off there. The third challenge, yes, good things come in threes and bad things also come in threes, is wrangling dependencies. The higher the number of dependencies, the higher the risk for potential conflicts. It might break things when you least expect it and when you least want to debug it, like Friday afternoon. But it's not the end of the world, and the cloud providers have not won. There are ways to address each challenge. Given limited resources for model serving, we can use, for example, a smaller quantized model instead of a full precision model. If we don't have access to GPUs, we can use CPUs. To deal with dependencies, we could use implementations that do not require as many dependencies or dependencies at all. So let's take a look at how the llama-cpp-python library solves these challenges. It's actually quite a mouthful, so from now I'm going to call it this library, so you know what I'm talking about. So this library is an open source library that offers a high-level API to integrate LLMs into your Python applications. It's built upon llama-C++, which is the original inference code written in pure C++ with no dependencies. I know it might seem like it's yet another wrapper around C++ code, but bear with me. It's also the official one, so let's take a deeper look anyway. This library is dedicated to running quantized models that are in the GGUF format. It's previously known as GGML, so if you see those terms, they're related. It works on most operating systems, and it's also pretty easy to install. Which it also offers the same OpenAI-like chat interface, which means it can be easily a drop-in replacement or a backup. So with this library, you can run models using a CPU only, and even upload some layers to the GPU. You can also use it as a web server to run your local models without internet connection. So it doesn't take much to code up a command line chat assistant that runs locally. In fact, here's one I prepared earlier. I actually mean to show you this. So the whole thing runs on a model that is 4 gigabytes on pure CPU. It was up and running in about 2 minutes. The chat state is managed as well, so it can remember what you guys are conversing about. You can also find out more on this QR code, but I think for now, let's move on. So the GGUF models are much smaller because they have been quantized to use a specific number of bits to represent their model weights. To quantize your own model from full precision, you would need to use the original CPP library. But alternatively, you could also try to find already quantized ones on Hugging Face. Chances are that this user, called the bloke, has already quantized one of your favorite models. So how does this help solve the challenges we saw earlier? As I mentioned before, the first challenge we face when serving LLMs is that they're too big for machines that we can afford. Sad, but true. Instead of the models in full precision, we can quantize them into smaller models. I think after Maria's talk, how many people are still unsure what quantization is? Okay, everybody unsure, a bit unsure. Okay, that's okay. So quantization is a process that converts continuous values into a discrete set of values. And for a more tangible analogy would be how we tell time. Time is continuous, and we use hours, minutes, or seconds to quantize time. Sometimes around 3 o'clock is good enough, but sometimes we want to be precise to the millisecond. In the context of deep learning, quantization is a model sorry, I lost my train of thought there. There we are, okay. So in the context of deep learning, quantization is a technique to reduce the computational and memory cost of running a model by using lower precision numerical types to represent its weights and activations. So these types usually have fewer bits and are less precise, so that take up less memory. For instance, instead of using 32 bits, a quantization type would use 8 bits or sometimes even 2-bit representations. So this would reduce the precision, but that comes with a trade-off in model accuracy. If we go on Hugging Face to look for a model's weights, chances are they're using floats 16s. This library would drastically reduce memory requirements by using quantized models. So for example, to serve the llama-cpp model that we saw earlier, instead of the 130 gigs, we're now looking at around 40 gigabytes. Of course, there's gonna be some kind of quality loss with quantization, and the amount varies, but you can get the most balanced results from a mixed precision approach that retains the precision for the most important weight matrices. So not everything, but just some. And I mentioned some quality loss before. So how do we know how much quality is affected after quantizing a model? A common metric to use is perplexity, which measures the uncertainty or surprise a model when predicting the next word in a sequence. So in this metric, lower is usually better. It usually means better predictive performance. And in this context, one would measure how perplexity changes with different levels of quantization. So to measure this, the model would run through a data set like Wikitext, and then we would follow this equation to calculate the metric from the outputs. And so Hugging Face has put together a neat little walkthrough that we can follow step by step. We can also find detailed comparisons in the community. For instance, like this one, for instance, that compares a few different 4-bit quantized models from different backends, like AutoGPTQ, XLlama, or the transformers load in 4-bit, on factors like perplexity, load time, memory usage, and speed. That said, perplexity does not usually tell the whole story. There are lots of feedback that mention empirically 4 bits is a good balance between memory and quality, but in reality is that there's rarely one size that fits all. It's impossible to tell until you try it out on your own specific task. So I'd say whether you're bound by accuracy metrics or deployment cost constraints, let your must-have requirements guide your setup. So that's our model size challenge pretty much solved. Our next one is latency and throughput. So overall model latency can be split into a few parts. We start with load time, which is loading the model into memory, and then followed by sampling time, which is choosing the next likely token. And there's prompt eval time, which is the time it takes to process the prompt before generating new text. And then finally, eval time, which is time taken to generate its outputs until, for example, the end of text token or a user set limit. So empirically, we found that load time for full precision models is much longer than that of quantized models. That should be pretty obvious. I guess it's that there's less to load, so that's great. And as for prompt eval time and eval time, these would vary a lot depending on the length of the prompt and the length of the output. This is why, while latency is a common metric for measuring the performance of most production systems, we don't usually focus on it as much for serving LLMs. Naturally, longer prompts and outputs would lead to higher latency, so the metric we're usually interested in instead is tokens per second, which refers to the output tokens generated per second by the model. This is where the library starts to get a little less exciting. We found that full precision models have higher tokens per second than their quantized counterparts, which means that you get slower responses from quantized ones. This is because quantized models are designed to reduce memory requirements, but not the computational times. So this observation matches the expected behavior. For example, in a benchmark done by Hugging Face, with the same model, the highest throughput deployment could have almost 10 times higher tokens per second than the most cost-effective deployment that uses the same 4-bit quantized version. But a single metric, again, is rarely enough to capture the whole picture. We need to bear in mind that LLMs from different families have different tokenization schemes, which may affect how this metric is calculated. Not all tokens are made equal. So for example, given the same prompt, the token count from Llama 2 is almost 20% higher than that of ChatGPT. This should be considered when serving LLMs of different families. Also, LLMs often power inference systems that are used by more than one user at a time. So, like, for example, having multiple concurrent users on a single chat service. We want to offer users a good experience by considering other metrics like time to first token or tokens per second per user, for example. Our third challenge is wrangling dependencies. So from version compatibility to constant updates to deployment complexity, it can be a bit of a nightmare. This library, from what we have seen, offers a way out of this dependency hell. First of all, the library installs fewer dependencies. You do need NumPy, but you don't need Torch or transformers, which I think for Torch has a lot of compatibility issues across versions. In terms of model deployment, this library only needs information from the gguf file, so that one single model file that you download, as opposed to, for example, using the transformers library, which requires extra files like tokenizers.json or config.json on top of the model weights. So using a single model file simplifies the whole build and deployment process a lot. And of course, there are a few caveats. There are a few things on the other side of the coin that we should also take into consideration. So the first one, I think, is that many libraries also wrap this llama-cpp library. One doesn't have to use the Python library. One can also directly access the llama C++ library. There are also other alternatives like ollama that offer similar abilities to serve quantized LLMs with a Python client. So compared to the C++ repo, this library also seems to have a bit longer feedback time, so improvements to the Python library aren't merged in as quickly. Second, for the model quantization, it's still a very active field of work, and it's a fast-moving field. So this library is only a year old. So it's not surprising that there will be some method or other library that achieves better performance than what this currently offers. So for instance, something called xllama v2 has been empirically shown to be faster in terms of inference compared to llama C++ on 4-bit quantized models. Third, so currently this library does not have a stable major release, and llama C++ is also in beta. This means that breaking changes can be expected, which may be a risk that some developers do not want to take on when considering production use, and factors like maintainability and backwards compatibility. But I don't know. I feel like that doesn't really stop anybody from using those. Like I think Polars is also 0 point something. Rough also is in the same boat. So fourth is that this library still requires a few dependencies like NumPy and package installation as before, so pip install. The far end of this spectrum is a more extreme solution called llama-file, which allows users to serve an LLM as a single executable file. And that was brought forward by Mozilla. So I think there's a spectrum here on what we're comfortable with. And of course, one more thing that would haunt developers and your security team is security. Most of us are likely aware of why Pickle is not the first choice, thanks to Ben's talk. I don't think he's here. When it comes to serializing data. Pickle led to the safe tensors format, which I think is also prevalent on Hugging Face models. And that's a format that avoided security problems with downloading and running untrusted Pickle files. There is a recent potentially exploitable vulnerability discovered in this GGML library, but fortunately a patch landed a few days later. All this is meant to point back to the fact that as developers, we must weigh the trade-offs and explore alternatives to make informed decisions and make sure that those decisions are aligned with our project's requirements and constraints. So when we look back at the 3 challenges of serving LLMs mentioned at the beginning of the talk, we have likely solved 1 and 3, more or less. We can use a quantized model, which is way smaller, and that translates to being able to use machines with smaller GPUs or even no GPUs. Deployment is also simpler because we're dealing with fewer dependencies and only 1 model file. But number 2, latency throughput, not nearly. The output tokens per second was usually a bit slower. I think that this is aligned with most engineering principles, where of the 3 given pillars between cheap, fast, and good solutions, we choose 2. Here we wanted low cost and easy to deploy. So we chose a smaller model and sacrificed on speed and a bit of quality. So in all honesty, there was really no speeding up of open source LLM serving. If anything, we slow down massively. But in the end, I hope that this talk helps you speed up the process of development and that you have fewer bugs and headaches when serving LLMs in the future. And that's it from me. Here's how you can find me later if you have feedback on the talk or just want to connect. Thank you.
Thank you so much. Any questions for Isaac? Super clear, no questions. That's great. Oh, yeah, there is. So.
Regarding this framework, right, so llama-cpp-python and multi-user, as far as I understand, when you have multi-user and you're offloading to GPU, you can't have multi-users because it loads into the GPU and then memory is full. Am I correct or am I doing something wrong?
Mm-hmm.
Are you familiar with this problem?
I think you mean when the same model is serving multiple requests from multiple users. Yeah, it needs to allocate memory for the inference calls for them as well. Yeah, we definitely got some errors from those. I haven't tried myself using just a CPU only solution, so I don't know. But it would be interesting to find out. Yeah.
A new thing to test out. Okay. Any other questions? Looks like no.